This is Lab 4, Spring Mass Data. Introduction. The focus of this experiment is to determine how to identify, calculate, and computationally model oscillation. The purpose was to use elements such as period of oscillation, Hooke's law, and potential energy to create a computational model of oscillation. Some of the main physics ideas were period of oscillation, Hooke's law, potential spring energy, and potential energy of gravity. The period oscillation was to determine what the K value would ultimately be, and then we would use that K value we found in the period of oscillation to apply to Hooke's law, to then calculate what our LO value would be, and then potential spring energy and potential energy of gravity also played parts in the spring oscillation. Brief overview. This lab demonstrates that the LO value for the spring is 0.00153 meters, and that K is equal to 5.745 Newton meters. Procedure. First, to use the tracker to analyze the given video of oscillation of a spring, export the data to an Excel sheet, modify that code to match the data in tracker, and then compare the two using tracker. So this is just a screenshot. You can see the oscillations that occur on both the X and the Y axis. So the system was a spring and the ball, and the surroundings was everything else, and the initial conditions of this was that the velocity was 0 and there was no oscillation, and the ball was being held into place, and it was at equilibrium. So I first needed to calculate the spring stiffness value, and we used that using this period of oscillation, where we determined that there were 6 oscillations, and from there we could determine what the K value would be. And then to determine the LO value, you take the initial, you take this 0.7 meters and subtract the mass, the gravitational, and what we found to be the K value, and that gave us 0.0153 meters. Coding. So going through the code, we had to modify quite a bit of it. Most of this, and this first code, was just mass, and then delta T, we had to make sure we had a very small value. The KS value, the spring stiffness, we found to be 5.745. Relaxed length, that was that LO value that we calculated earlier. And then we had to change the L and the L hat and the S values. And then coming over here, K was half the ball mass times the magnitude of the ball velocity times 2, and then the gravitational potential energy was just the ball mass times the gravitational times ball position y, and then the US value, the potential spring energy was half KS and times S times 2 as found in the code, and then the total energy was the sum of all of these. And then we can go through this and see the multiple coding elements that we had to modify. And then the actual code itself gave me this graph, which I know is very wrong. Similarities at the end, there were similar oscillations over here. This is kind of what I'm referring to. And the difference is that tracker had many more oscillations. What does this mean for your model system? Is the energy principle satisfied? Justify your answer by discussing briefly your plots of energy changes. No, because my graph did not come out right. If there was more oscillation on my red, blue, and green lines, and my orange line was straight on the x-axis, the energy principle would be satisfied. Using the data you obtain in tracker, make 2 separate estimates of oscillation periods, first by estimating the period of oscillation from the X position data, and second by estimating the period of oscillation from the Y position data. Compare the 2 estimates and discuss. The X position would be the 1.662 seconds as previously shown in the slides, and I believe the Y would be the same since the oscillations go hand in hand despite their axis. Possible errors. My code was definitely incorrect, but as it was going through the motion for the final graph, it would oscillate, so I'm not too sure why the oscillations didn't present themselves in the final graph. Conclusion. In conclusion, this lab demonstrated to us how to analyze, computate, and create models for oscillation.